everyone, today I'd like to introduce Service-Oriented Robot Software Development Framework. Our framework has been developed by researchers of Co-Design and Parallel Processing Laboratory in Seoul National University in Korea. In the near future, it will be common for a user to make different kinds of robots work together in various fields. Unfortunately, it is very difficult to realize this vision because programming each robot considering the resource and energy constraints is challenging. On top of that, it is not easy to specify the mission scenario at the user level. We identify 4 requirements for desirable software design methodology of cooperating robots. At first, the software design should be independent of robot hardware platform. Also, the resource requirements should be minimized. What's more, those who lack knowledge of the robot's hardware and programming language should be able to specify the mission of robots easily. In the end, a collaboration of robots and dynamic behavior could be expressed intuitively. To satisfy this issue, we propose a novel software development methodology by separating 4 levels of abstraction. The first step is mission specification, which is the highest level of abstraction. A casual user can express the mission scenario with new scripting language. It can express team configuration and service-oriented programming. Next step is strategy description. It provides more information on how to perform services and how to specify non-functional requirements. And then, task graph specification is the next step. We use an extended data flow model for task-level behavior specification of each robot. Unlike mission specification, we assume that the internal definition of a task is developed by a professional programmer. The final step is code generation step. The actual robot code is automatically generated from the extended data flow model. For mission specification, a new scripting language is devised to make it easy for casual users to learn and use. The scripting language can express team configuration, service-oriented programming, multitasking, and dynamic mode change of operation. To our best knowledge, no existent script language has such expression capability. After specifying team formation, we can express their behavior like this table. Each cell in the table is service, which abstracts the function each robot can perform. We also allow a user to define a composite service which executes the primitive services sequentially. Multitasking specification is not easy to express in popular script languages, but we adopt the notion of plan. Multitasking is represented by mapping one composite services per plan. A robot may have multiple operating modes depending on the environments and the user request. The generated event in the composite service can trigger a mode transition. In our framework, we use the model-based task graph specification to express the internal behavior of each robot. Synchronous data flow model is a popular model. It has restricted execution semantics so that it can analyze the application behavior at compile time. However, its expression capability is severely limited, so our extended model uses finite state machine to represent dynamic behavior and a special type of task called library task to manage shared resources among multiple robots. This is an example how to specify the robot behavior using task graph model. Each task is a software component that performs the services specified in the mission script. Each sensor input task is triggered periodically and the sensor value is transferred to the control task after being filtered. The control task decides which algorithm or actuator is executed, like brain. There is a large gap between two abstractions, mission specification for casual user and model-based task graph specification. To fill this gap, an intermediate level of abstraction called strategy description is added. In this layer, a high-level service specified in the mission script is refined into a set of lower-level services that can be mapped to the task in the task graph model. And non-functional requirements that are not expressed in the mission script can be specified in this layer too. Assume that we have a mission script like the left side. We use move service, but we can't specify which algorithm is used in detail. In strategy layer, we describe how to move, and we added adaptive resource management policy. In this example, we check the battery level and adjust the execution period of sensing. To verify our framework, we conduct one example of the cooperative mission. Two robots are given the same mission script but use different algorithms to perform the mission based on the strategy description. We want robots to go to the specific point. One robot is controlled by an operator manually in the remote control mode. For this robot, we can specify internal behavior as shown on the top side. On the other hand, other robots operate in the autonomous moving mode to follow the robot like this task graph. You can check how real robots move. In University Booth, we're gonna demonstrate our framework using different kinds of scenarios. Thank you for your attention. See you in DAC.